So we will continue with the design of the grid floor by IS456 method. So in the earlier video, I had explained how to dimension the T beam or the rib portion of the grid floor, and also how to design the top slab portion. Now in continuation with that, we will take up the design of the T beam or the rib portion now. So this is the section we got. Earlier we have got this section. So this is the slab portion. So this beam and slab are cast monolithically. Therefore, the beam is acting as a T-beam. Now the dimensions of this T-beam section are fixed like this. Width is 150 mm. All the dimensions are in millimeters. And the effective cover I have taken 50 mm. Overall depth including the top slab is 650, and the thickness of top slab 90 mm. So, and the depth of this rib portion is 510 plus 50, that is 560 mm. So these are the dimensions we got earlier. Now one more dimension we need, that is the width of this flange portion, because a portion of the slab, this is the top slab, a portion of the top slab acts as a beam. So that width of that slab which acts as a beam, that is called as your flange portion. The width of the flange, which is denoted by BF1, it is given by this formula, B plus 12 times TF. So where B is the width of this beam, which is 150, plus 12 times thickness of flange is 90 mm. So thickness of flange is nothing but it is the thickness of the top slab. Now it comes out to be 1230 mm, which is less than 1500 mm, which is the grid spacing. That means if this value, if BF is greater than that grid spacing, that is 1500 mm in this case, then we have to restrict that BF to 1500. Please note this point. So because it cannot be greater than 1500. So this is what is the width of line is. Then now we have to design the section. So the T-beam section. For that, we don't know where the neutral axis lies in the T-beam section. This design is similar to your design of T-beam in RCC section, which you have studied in your BE course. So what we do is, initially we will assume that the neutral axis lies at the bottom of the flange. That means at this level. It lies at this bottom of the flange. Assuming that we are going to calculate the moment of resistance of the section, which is denoted by mu dash by this formula, 0.36 FCK BF into D minus 0.42 TF. This is for Fe 415 steel, so which is obtained from this IS456. This equation you can get from IS456. Now substitute the values. 0.36 into FCK is M20 compared here into 20, BF is 1230 mm and TF is 90 mm into D is the effective depth of this total TB, which is 600 mm. 650 minus 50, 600 minus 0.42 into, once again TF is 90. If you simplify this, you will get 448.1 into 10 power 6 Newton millimeter, or it is 448.1 kilonewton meter. Now you can observe that this whatever moment of resistance we have got mu dash, it is greater than the design moment. Design moment we got 256.94. 256.94. You can refer the earlier video. Mx My value we have got. In that Mx value is 256.94 along the shorter span. So now we can see that this is greater than that 256.94 km meter. Therefore, we can conclude that the neutral axis lies within the flange. So within the flange it lies somewhere here. It lies somewhere here. That is the neutral axis. So just to identify where the neutral axis lies, whether it lies within the flange or outside the flange, we have to assume initially that the neutral axis lies at the bottom of the flange at the interface. Then we have to calculate that mu dash value. So compare that mu dash value with the design moment, which is so 256.94. We have got 448.1. So since it is more than that, so what we can say is the neutral axis lies within the flange. Now, once you get this value of mu, you can calculate this mu by BD square, and for a given combination of FCK and Fy, so you can always get the value of percentage of steel PT. PT you can get. So from that PT, you can get the value of ASP from SP16. So you can directly use SP16 for calculating the quantity of steel reinforcement required by knowing these values. So once you use that, you are getting 1229 millimeter square as the tension steel. So assume 20 mm diameter bars, you have to provide 4 bars, which gives the area of 1256, which is slightly more than this. Similarly, in the longer direction, this is in the shorter direction. Actually, this whatever 256 you have got, this is in the shorter direction, and in the longer direction, what moment you have got is my. So which is nothing but your mu in this case 161.66. So for this also we have to design the reinforcement in similar manner. So you have to calculate mu by BD square, and for the given combination of FCK Fy from the respective table in SP16, you can get the PT value, and then you can get the AST value as 763 millimeter square here. So assuming 20 mm bars, 3 bars you can provide, which gives a reinforcement of 942 millimeter square, which is slightly more than this. Now this is the design for flexure, that is designed for bending moment in either direction. So then we have to check for shear also. Normally in the case of slabs, shear is not a governing factor, but again we have to check for that. So maximum shear can calculate along the shorter span by this formula Q1 into Lx by 2, where Q1 is equal to QR power 4 divided by 1 plus R power 4, where R, this R is nothing but Ly by Lx. Ly by Lx is R. The ratio of longer span to shorter span, which comes out to be 1.5 here, 18 meter by 12 meter, which is 1.5. So you can take R as 1.5. This Q is the load coming on the beam, which you have calculated as Q is nothing but WU coming on the beam, which is 20.04. I have explained in the earlier video. So 1.5 to the power 4. Divided by 1 plus 1.5 to the power 4 into Lx is 1 meter shorter span length divided by 2, you are getting 100.4 kilonewton. 100.4 kilonewton. Similarly, you can calculate maximum shear along the longer direction. So along the longer direction, the formula is Q2 into Ly by 2, where Q2 is Q divided by 1 plus R power 4 into Ly by 2 you get. So similarly, if you substitute the values and simplify, you get 29.76 kilonewton. So you can observe that. So maximum shear in the shorter span is greater than the maximum shear in the longer span. So now you can design for higher value. So design shear for higher value. So higher value is 100.04. You can take a higher value. So that is, I will take it as VU. VU is 100.4 kilonewton. Calculate tau V. Tau V is nothing but VU by BD. So all these you know from SP16. You can calculate these values. Nominal shear stress tau V, VU by BD. So B here is 150 for this beam. D is 600. So you get 1.116 Newton per mm square, and the percentage of steel provided is 1256. 1256 divided by that BD. In AST divided by PD into 100, you are going to get 1.4%. So for 1.4% of steel, this value of TOC is you can get from that table, and in this case you can see that this TOV is very much less than TOC. Therefore, what you can say here is nominal shear reinforcement is sufficient. What is nominal shear reinforcement? Normally we provide 2 regular 8 mm dia bars, stirrups at 300 mm center to center. That is the minimum or the nominal shear reinforcement. So once you design for both flexion and shear, you can just show the reinforcements detailing in the cross sections. Along the shorter span, it looks like this. So here you have the T-beam portion. So total overall depth is 650, effective depth is 600. This is 90 mm, this is 150 mm. So you are going to provide 4 bars of 20 mm diameter. So this is along the shorter span, and at the top you are going to provide 2 of 12 mm diameter bars. as hanger bars. They are called as hanger bars. So for just for stability. And in the slab portion, already we have designed it in the earlier video. I had explained. So you have 6 mm dia bars at 250 mm center to center in both the directions. In both the directions. That is the shorter beam section. This is the longer beam section. In the long beam section, the only difference is this. So ASP is 3 of tar 20. So 20 mm bars, 3 numbers are enough, and the remaining reinforcements they are same. So in longer span. So this is how we can design the grid floor by IS456 2000 method. So we have designed top slab portion. Then we have designed the rib portion. Then analysis we have done for the rib portion. We have calculated the maximum bending moment and all. Then we have designed the T-beam, and then we have checked for shear, and the detailing has been explained.